Training to inference, GPU to NPU and LPU, the rise of non-Nvidia chips.
This diagram from the EU AI Act shows how regulatory bodies define an AI system. It's a dense web combining model architecture, training data, and human preferences. Trace these software pathways back to their origin, and they rely on one physical engine: AI compute. Compute takes a massive physical form: warehouses filled with thousands of metal racks, pulling gigawatts of electricity off the power grid to process endless streams of data. This physical infrastructure dictates the speed and the cost of every AI model currently under development. This blueprint shows the difference between a CPU and a GPU. CPUs handled sequential logic, but in 2012, researchers realized GPUs possessed a massive capability for AI. Neural networks process thousands of matrix multiplications simultaneously. A GPU's parallel grid perfectly matches this math. Look at NVIDIA's 72 GPU Blackwell rack. They scaled this parallel advantage into a $3 trillion valuation, selling systems for $3 million each. Their dominance is protected by CUDA, a proprietary software platform. Porting models from CUDA to a competitor is a massive technical hurdle. This diagram compares the GPU to a custom ASIC. A GPU is a Swiss Army knife, highly flexible but expensive. Running specific AI tasks millions of times a second globally means a flexible $40,000 chip becomes a massive drain on capital and power. The general-purpose chips that birthed the AI revolution are becoming too expensive and power-hungry to sustain the next stage of its deployment. The AI lifecycle has two phases. Left is training, feeding massive datasets into a model. Right is inference, using that model to generate real-time results. NVIDIA dominates training, but compute volume is shifting towards inference, requiring hyper-efficient chips instead of general-purpose GPUs. This slide highlights the hyperscaler revolt. Cloud giants like Google and AWS are building their own silicon to avoid the premium costs of buying millions of third-party GPUs. Here you can see Google's TPU, or Tensor Processing Unit, next to an NVIDIA component. Google hardwires these custom ASICs for the exact mathematical operations their specific models require, stripping away general-purpose architecture to cut power use. Amazon's Trainium 3 chip follows a similar logic. By moving hardware design in-house, AWS claims it can achieve a 50% lower cost and 40% better energy efficiency than comparable NVIDIA alternatives. To maintain their profit margins, trillion-dollar tech companies are vertically integrating their hardware, building the very infrastructure they used to rent or buy. The need for cheaper inference is breaking traditional chip design rules, leading startups to experiment with entirely new form factors. Cerebras has abandoned traditional chip sizes, keeping an entire silicon wafer intact to create one massive engine. This maximizes compute area and removes the delay caused by passing data between separate, smaller processors. In a bold hardware move, Grok developed the Language Processing Unit, or LPU. This architecture is designed specifically for running large language models at high speeds, outperforming traditional GPUs on those specific tasks. In a massive industry shakeup, NVIDIA recently announced a $20 billion deal to acquire Grok. They are acquiring specialized inference architectures to ensure they retain control as the market moves past the initial training phase. The final destination is the edge. This SoC diagram shows neural processing units, or NPUs, integrated directly into phones, laptops, and cars. On-device AI ensures complete data privacy, removes latency, and allows autonomous devices to function without a constant cloud connection. AI computation is decentralizing, shifting away from centralized cloud services and into a fragmented ecosystem that lives inside the devices we use every day. This map of the foundry monoculture shows the industry's biggest risk. NVIDIA, Google, and Apple all rely on a single manufacturer, TSMC in Taiwan. This creates a geographic choke point for the global AI boom. The U.S. CHIPS Act is a response to this risk, funding a push to return advanced fabrication to the United States. This includes new TSMC and Intel plants currently under construction in Arizona. Even with domestic manufacturing, the ultimate bottleneck is the electrical grid. This illustration shows the server racks wired directly into the transmission towers. Securing the megawatts of power required to keep these data centers running has become a competitive requirement for the next wave of AI development. Building energy infrastructure is now as critical as manufacturing the chips. This timeline shows the shift in the industry. The early boom was a monoculture of general-purpose GPU clusters. The mature era is a diverse matrix of specialized ASICs in the cloud and hyper-efficient NPUs on individual devices. The hardware market has matured into a complex ecosystem. Success no longer depends on building the fastest general-purpose chip, but on optimizing silicon for specific locations, power constraints, and mathematical purposes.